Good morning. Good morning, everyone. Thanks very much for the opportunity to talk at this important summit today. As you can tell from the title of my presentation, I'm going to be taking kind of a high-level view of nutrients. I'm going to be talking around that challenge that you've already heard about already from our first two speakers, of managing nutrients for agriculture, food production, food security, and reducing environmental impacts. I'm going to draw on long-term data in relation to global trends in nutrient use, and I guess that will primarily be drawing on issues associated with fertilizer use. I'll talk about some national, local and industry-related trends there as well. I wanted to spend the last section of my talk relating to what I think we've really been doing very well in the last decade or so in relation to how we better refine our information and the application of that information in relation to fertiliser decisions. And again, I think our previous speakers have really done a great job at introducing some of those, and in fact a couple of my slides have already been stolen, so we'll skip through some of that. But we're talking around nutrients, and nutrient is the title of our forum, and I thought we probably needed a bit of a definition. So who's brave enough to give me a definition of what a nutrient is? Okay, so we have a room full of nutrient management experts. There's not a single person who's prepared to put their hand up. Okay, fair enough. Okay. So a nutrient is a compound or an element that organisms require for their function and their growth and their reproduction. And if you're a non-autotroph like ourselves, then we acquire nutrients through the ingestion of food, of course. But if you're an autotroph, like a plant or a microbe, then you use very simple elements or compounds and then build more complex ones. And the 16 essential elements for plants, of course, are well known and listed here. And the ones I'm primarily going to be talking about are the ones that have already been mentioned, nitrogen and phosphorus. And the reason for that is, of course, they are the most limiting in relation to our agricultural production, terrestrially limiting and aquatically limiting, and therefore they're also the ones that create the greatest environmental impacts in relation to when they leave the productivity cycle and end up in that environmental cycle. So it never ceases to amaze me that we can pretty much almost feed the population of the planet with agricultural areas that make up such a relatively small overall proportion of the terrestrial land base. Since 1960, we actually added to that agricultural land. There was almost a linear increase in the amount of agricultural land, and that was primarily through deforestation, through drainage of wetlands, through increases in irrigation regions. But since about the mid-1990s, we've seen a trend towards declining availability of land. So the drivers of that, of course, are desertification and increasing urbanisation, amongst other factors. The estimates are that we're going to need something in the order of 50% more food by the year 2050 to feed a population of about 10 billion or so. And so clearly nutrients, which are a key part of driving extra agricultural production, is going to be an integral part of that. We've known about the importance of nutrients and processes around enhancing nutrient recycling in agriculture for hundreds, if not thousands of years. But it's really important to note that the industrialised process of creating highly soluble, highly transportable, plant available and really very cheap nutrients can actually be measured in decades. So there's this enormous change that's been going on in a very short period of time. And we'll start off with 1960, a very important date, because that was the year that I was born, and apparently Nick Drew was born on that year as well, so it was a pretty good year, 1960. And at that point in time, there were about 2.5 billion people on the planet. We contrast that now to 7.5 billion, and as I say, an estimated 10 plus in the not too distant future. And over that period of time, we saw a very dramatic change in our agriculture. Many of you would be familiar with the stories of the Green Revolution, which kicked off in around 1960 and went through to about the 1980s or thereabouts. And that was primarily around enhancing enhancing our agriculture through improved plant breeding processes, but very much about the input side of the equation. And that was driven primarily by the industrialisation process of manufacturing synthetic fertilizers, and of course nitrogen fertilizer being a very major part of that process. So you can see a very dramatic increase in the amount of nitrogen that is used. In fact, the estimates are that we've quadrupled the amount of reactive nitrogen on the terrestrial side of the planet over that period of time. So as Eric Davison says, fertilizer use is absolutely essential in terms of feeding a growing world population. In fact, you have a look around in the room now, imagine 50% of the people in this room would not be present if it was not for those advances in relation to the production of synthetic fertiliser. We've seen the same sort of growth in phosphorus and potassium as well, although it's important to note, and I'll show some data later, that this is quite regionally based. So the trends with nitrogen are fairly uniform, but for the other nutrients they seem to be quite regional in their demand. So what's the problem? Well, the issue is that our biological systems, and of course farming is farming biological systems, are very inefficient in terms of the overall capture of the nutrients that we actually introduce within those systems. So the global efficiency of nitrogen use is estimated to be around 40%, and for phosphorus it's estimated to be around 25%. So when we do these nutrient use efficiencies, we usually measure them as the basis of what we're removing in agricultural product versus what we're importing or applying. Okay. It's not a direct connection to environmental impact. So for nitrogen, for example, if we're also accumulating soil carbon within those systems, then the likelihood would be that that nitrogen would be encapsulated with that carbon. And so we can accumulate nitrogen within our agricultural systems. On the other hand, with phosphorus, we understand now, much better in fact, the role of phosphorus buffering and the absorption processes that occur when we apply phosphorus to our soils. And we'll be hearing, I'm sure, talking a fair bit about that today. Another really substantial shift has been the very dramatic increase in the amount of animal protein that we've been consuming. So the estimates there are an almost linear, well, it actually wouldn't be linear, would it? It would be an exponential increase in the growth of intake of animal protein compared to crop protein, with a 5% per annum over the last 50 years growth pattern. Perhaps it's not surprising that around 2/3 of agricultural area on the planet is used for feed livestock when we think about the broad acre, low input rangelands that are available to us. But I find the statistic that 60% of all crops now grown on the planet are actually passing through animals before we get to ingest them, is an interesting process in terms of an extra step of inefficiency that we're putting in our systems. And as you've already heard, with a limited amount of land, our agricultural systems are in fact becoming more intensive. It's certainly the case for our animal industries, with a whole host of issues associated with manure production. And so an interesting statistic is that actually the total amount of nitrogen and phosphorus excreted by these animals per annum is the same as what is manufactured through synthetic fertiliser production each year. So I'm really not going to talk much about the environmental implications. We've already heard in detail about some of those issues. We know about phosphorus and nitrogen and how it's moving into waterways at a range of scales. We know about nitrous oxide and the contributions that it's making as a potent greenhouse gas. We perhaps know a little less, or understand a little less, around the issues of nitrogen volatilisation in Australia. It's not a big ticket issue, or certainly not recognised here. But in Europe and in the US, where nitrous oxide, particularly from animal production, ammonia volatilisation, particularly from animal production, is a very major contributor to haze and respiratory illnesses through the combining of ammonia with other particulates in the atmosphere. A really good example of where we're at in terms of getting the balance right between food security and environmental impacts is given by China, and many of you would be probably familiar with this scenario. So in the 1970s, there was a rapid increasing population in China, and the government was extremely concerned about overall food security, so commensurately they decided that they would subsidise the use of nitrogen fertiliser. It's interesting to note now, with those subsidies still in place, that China uses a third of the world's manufactured nitrogen fertiliser on 9% of the world's arable land. As this graphic by David Paulson clearly demonstrates, the process was actually very successful. Between 1918 and 2010, we saw a 70% increase in the total amount of grain production, but this was driven by a fourfold increase in the amount of nitrogen fertiliser that was used. There are obviously a lot of other changes that were going on in China as well, not the least of which, of course, was urbanisation, which actually provided money in people's pockets to be able to buy synthetic nitrogen fertiliser and then be able to use that in a much higher rate than would normally and economically be required. So the consequences of that was not only a whole suite of those environmental issues, but also reductions in yield due to things like crop lodging. It's interesting to see that the total volatilisation loss of ammonia in China is actually greater than the total amount of nitrogen fertiliser used in the continent of Africa. And I think that statistic really drives home this message around the disconnect between applying too much nutrient to overcome particular issues and then having continents like Africa where significant portions of that region suffer nutrient deficiency, phosphorus and nitrogen deficiency, and so that need for more fertiliser inputs into those systems would surely be overcoming some of the food security issues that they're challenged with. So we'll switch more locally now to Australia. So Australia's agriculture contributes around 4% of gross domestic product, about 18% of export earnings. We claim to have 500 million hectares of agricultural land, which is about 60% of the total land area. But actually the reality is we only have 50 million hectares of arable land. And so you can see the various enterprises and the contributions that they make in terms of export earnings, with the big tickets being beef and grains. Dairy and sugar are also important, and specifically so regionally, so dairy for Victoria, for example, and sugar for Queensland. If we look at where the fertiliser actually goes, around 60% of Australia's total fertiliser use ends up in our broadacre cropping, 25% ends up in our pasture-based systems, and the remaining 15% is fairly evenly split between horticulture and sugar. Our industry spends about $3 billion a year on fertilisers, and that may seem like a sizable amount, and yet we use 1% of global fertiliser use. So we're a pretty small player in terms of the amount of fertiliser that we actually use. If we look at the trends in use, you can see a small decline over the last 15 years or so in the amount of phosphorus, potassium and sulphur that is being used at a national level, but a kick up in the amount of nitrogen that is being used. And I think that sort of followed after the millennia drought and the implications that had for fertiliser use, and again in confidence, I guess, particularly in the eastern states. So we can have a quick look at Western Australia now, and I'm certainly not going to lecture you guys about agriculture's contribution in Western Australia. The big industries here, of course, are the same: cereal production and meat production, with other industries like dairy having a lower priority. But the overall fertiliser use is about 30% of the national amount of fertiliser that is used, and those trends over that last 15 years follow the same sort of national trends. The kick up in nitrogen there happened in around 2010, so there seems perhaps to be a lag, but no doubt driven, I guess, by increased confidence in prices, etc. So if we think about where the fertiliser is going, the two big tickets are the broadacre cropping areas and the pasture areas, and I wanted to talk about some examples associated with that. So it's interesting to note how we benchmark against other grain-producing regions of the world, and the way that we do that is through the calculation of what's called a partial nitrogen balance. Another way of describing that is nutrient use efficiency or nitrogen use efficiency. That's the ratio of the amount of nitrogen that was removed in product versus the amount that was applied in fertiliser. So here's a list of all of the major grain producing regions of the world. And the black line that's shown there is the global average, which is about 65%. So a nitrogen use efficiency of about 65%. Australia there in green, is it green? Anyway, over here, is about 82%. And I talked about China before, and it's just under 50%. So you can see how we benchmark. And although it doesn't look like we're actually on the top of the pack, you'll notice that the remaining 6 to the left-hand side are in fact all above the red line. So what that means is that they're actually removing more nitrogen than they're actually bringing on. So they're mining nitrogen from their system, and that's not a sustainable position. You don't want to be removing more than you're actually bringing back in, because by degrading nitrogen, you're also degrading soil carbon, and so the likelihood will be that you'll be degrading their soils. Now there are some assumptions around this, and some of them work well for us and some of them don't. So we're not applying, in any broad sense, animal manures into these systems, and some of these countries certainly do. We have historically used legumes as a means of providing nitrogen into our system, and there are still plenty of legume rotations that are used in our cropping-based systems. And we also are assuming a standard crude protein content of the grain. Australia's grain crude protein content is generally lower than most other regions, and the reason for that is we tend to use fairly low rates of nitrogen fertiliser within our cropping systems. So the other example I wanted to talk about was pastures and how effectively we're using nutrients in pastures. And if we're talking about nitrogen, then primarily we're talking about nitrogen applications in dairy pastures. We know also that as we intensify our systems, our nutrient fluxes are increasing, but it's unclear as to whether we're actually removing an equivalent amount. So there's a question around, as we intensify our systems, and we've certainly been doing that since deregulation, and the growth in confinement-based systems that has been happening, we're interested to know what's happening to those nutrients that we're bringing on board. It's interesting to note, as I've said here, that our farms are getting fewer in number but larger in size. And in fact, 50% of the milk that's produced in Australia now comes from just 15% of the farm. So we're interested in this nitrogen recovery story as the industry intensifies. So this is data over the last 22 years, and if you look at the red line on the bottom, you can see that in fact, for the industry average dairy farm, we have actually been increasing the amount of nitrogen that is recovered in product, primarily in milk exports on a per hectare basis. But this has come with substantial increases in the amount of nitrogen, and it's not just fertiliser nitrogen that's being applied there, it's also nitrogen that's being imported from all of those crops that are actually being grown elsewhere, and that extra nitrogen is being brought on board. So the implications of that is that we've got an increase in the net nitrogen surplus, so that's the nitrogen that's lost to the environment over that period of time, and a trend towards declining nitrogen use efficiency, which was at around 40% and now operating for the industry average farm at around 26%. If we switch nutrients now to phosphorus, and you've already heard about the work that David Weaver and his team have been doing over a long time, and this is some data from David that shows phosphorus use efficiency across a number of industries, and I think this, where are you, David? You hear something? So I'm assuming that this is all Western Australian data rather than national data. It is. And so you can see the diversity of efficiency of capture of that phosphorus, ranging from just under 50% down to 11%. What's interesting to me is there's really not a relationship there between the intensity of the system and that efficiency. That's really important. So you can see the fairly extensive cropping-based systems have an efficiency of 50%, whereas you go to sheep, which is a very extensive grazing-based system as well, it has a low efficiency of about 11%. What's important also to recognise is that there's a big diversity in relation to individual enterprises. So if you look at the dots on the box and whisker plots, which are individual farms that are lying outside the normal distribution of the data, you can see that if we choose cropping, you can see that there's some farms that have a phosphorus efficiency of close to 10%, and then there are others that actually have efficiencies above 100%, where they're actually mining phosphorus from the system. So it's really important to recognise that yes, there is big differences between enterprises, but there's way bigger differences between the operations within the system. And that's where our scope for improvement really lies. So I just wanted to finish off talking about some of the technological advances that we've made over the last decade or so. And I really wanted to highlight some of the things that I personally believe that we've done really well. And I think we've got an awful lot to be proud of, and I think Western Australia has a substantial amount of information, technological advances and improvements that they've made over that period of time, perhaps more so than any other states. We've had well-resourced research programs delivering specific sets of information that have been highly relevant. The work that was done, I think, and the recognition that we need to pull together as much information as possible led to the development of a couple of programs you may be familiar with called the Better Fertilisers for Pastures and the Better Fertilisers for Croppings program. And the objective of those was to pull together as much research field-based information as we could so that we could interrogate that and also explore that data and come up with better sets of fertiliser recommendations from soil test calibrations. And an example of that would be the refinement that we've made in the soil test Colwell P, where we've now linked that successfully to phosphorus buffering within soils, in this case the phosphorus buffering index, and we now can have a much more refined fertiliser recommendation, a much better definition of the overall soil test targets that are required when we link those two critical pieces of information. We've already had a slide almost exactly the same on this, and I won't dwell on that, other than just highlighting the fact that I think we're getting pretty smart about how we actually deliver information to both farmers and advisors. So rather than a telephone book of soil test data with a whole suite of decimal places, we can now actually simplify the delivery of that using pretty colour-coded maps and make it quite easy for people to actually identify where their requirements are likely to be. And I also want to add to that that the importance of animals within the landscape is another really crucial part of that. So working with farmers and advisors around how your management overlays with those maps often really lights some light bulbs in terms of how people better understand nutrient cycling within their individual farm. Another area that I think we've really made some inroads has been the identification of risk profiles within the catchment or within sections of the landscape. And in this particular example, if you just had a Colwell P soil test, that was the only piece of information you had, you would be very poor at predicting the risk associated with nutrient loss, phosphorus loss from that. But if we link that to things like the retention capability and the transport mechanisms within the catchment, an understanding of management, we can quickly highlight the areas where we need to put special attention to minimise those nutrient losses. And the last example I wanted to give, and it's certainly not conclusive, is the fact that we've really started to get smart about how we integrate multiple pieces of information. So it's easy now for us to go onto the web, we can map farms, we can bring other layers of information such as soils and climates together, we can overlay management decisions, and we can use all of that in a fairly seamless way to develop indicators such as whole farm balances or in fact nutrient balances at a paddock level, where we can actually download that information and make much more informed decisions. There's been some mention of the use of enhanced efficiency fertilisers, and I think this area is actually going to grow in the next decade or so. A lot of the enhanced efficiency fertilisers that are available have been through the use of inhibitors, microbiological inhibitors within soils. They have a place, but at the minute the cost-effective nature is somewhat questionable. I think we'll see further developments in things like coatings of fertiliser that actually better release nutrients to match the plant's demands. So that's on the demand side. So I think that that's an area that you'll hear a lot more of into the future. And I think you'll also see sort of the marrying of different societal challenges. We're certainly seeing this in Europe and in the US, where manure loads are now not just being used and valued for their nutrient value, they're actually being valued as a source of feedstock that's going into bioenergy production. So a few take-home messages. I hope I've convinced you that nutrients are essential and will in fact continue to be essential for food security for the planet. That we have these significant regional challenges and we need to be smarter about how we use those nutrients, not only from a cost-effective and production capability, but also from an environmental capability as well. It's expected that growth in fertiliser use will continue, and I think nitrogen in particular is likely to grow. But similarly for the other nutrients, there seems to be an expectation of growing global demand. Intensive industries have much greater nutrient fluxes, and on a per hectare basis, they have much greater nutrient losses. But that doesn't mean that our extensive industries are not also running into issues associated with low efficiencies and retention and also loss factors associated with that low efficiency. I think we really should pat ourselves on the back in terms of the work that we've been doing over the last decade or so, and I've alluded to a number of areas, and I'm sure there's many more that you can talk about yourselves. But I also believe that we're going to need some major step changes in technologies to actually really tighten that overall nutrient cycle so that we can overall increase that global nutrient efficiency. And just to drive that message home, a reminder that 7 of the 17 United Nations Global Sustainability Goals are directly related to the need to increase nutrient use efficiency. So, thank you very much.
Thank you.